Hi guys! In this video we're going to be looking at Introduction to Phase, Phase and fractions of wavelength, in phase, out of phase and an antiphase, phase difference, and we're going to finish with a summary. So we're going to start off by actually introducing the idea of phase, and we're going to try and understand what phase is before we look at it in more detail. We can introduce a property of waves by looking at hands moving around a clock. So for example, we're going to consider the minute hand, which is this orange hand here, and we're also going to consider the hour hand, which is the pink hand here. And by considering how they go around the clock, we'll be able to understand this property of waves, which is called phase. Imagine two clocks are wound to 12 o'clock and then set to start ticking, but one clock is started after the other. So for example, let's consider the clock on the right, and let's say this one was started first. So we can see after starting this clock, after a certain amount of time has passed, it reads the time 12:15. So we can see it's 12:15. Now let's consider this second clock, which we started later. So this one lags behind the first one. So when we read a time of 12:15 on the first clock, we read a time of 12:05 on the second clock, because the second clock was started after the first clock, so it's lagging behind it. So when we read off the time that's shown by each clock at the same point in time, we find they display different times. We say the phase of a hand is the portion of the cycle it has completed. We can measure it in minutes, or better, as an angle from 12 o'clock. So if we're considering the minute hand here, and we're considering the portion of the cycle it has completed, which is what we refer to as phase, we're going to measure this from 12 o'clock. So if we want to measure the phase in minutes, we would say that 15 minutes have passed. So we can see that the minute hand has completed 15 minutes out of the 60-minute cycle it takes for it to do one whole revolution. So it takes it 60 minutes to go from 12 o'clock round the clock back to 12 o'clock, but we've only completed 15 minutes of that total of 60 minutes. But we can also measure phase as an angle. So we can measure the angle that the minute hand makes with this line on 12 o'clock, and we can see that that's a 90-degree angle. So the phase is equal to 90 degrees. And we can also write this in radians. So if we write it in radians, the phase is equal to pi/2 radians. By measuring phase as an angle, the hour and minute hands will have the same phase when they point to the same part of the cycle. So for example, if we consider just our minute hand here, we can see that when it points at 3, it makes an angle of 90 degrees with 12 o'clock. So its phase is equal to 90 degrees. And if we look at the hour hand and measure its angle when it's pointing at 3 o'clock, and we measure its angle from this line at 12 o'clock, we again see that its phase is 90 degrees. So although a different amount of time has passed for each hand, so for example, the minute hand will take 15 minutes to reach 3 o'clock, whereas the hour hand will take 3 hours to reach 3 o'clock. The portion of their actual cycle they've completed is the same. So the phase is the same, even if it's taken them a different amount of time to reach that phase. And the reason we're measuring the phase of the hour hand and the minute hand in angles rather than minutes or hours is because this allows us to compare their phases, because we're using the same unit for both. And this is why we always measure phase as an angle in waves. The phase difference between the minute hands on two different clocks is the angle between them. So for example, let's consider this first minute hand, which is pointing at 3, and we can see that its angle, and therefore its phase, is 90 degrees. So the angle here is 90 degrees, so we say that its phase is equal to 90 degrees. But now let's consider this other minute hand on another clock, and let's see the angle that it makes with 12 o'clock. So we can see that this angle is 30 degrees because it's a third of 90. So in this case, the phase is 30 degrees. Now, if we want to calculate the phase difference, we can simply calculate the difference between the two angles. So the phase difference between these two minute hands on the different clocks is just given by 90 minus 30. So it's going to be equal to 60 degrees. Because the minute hands on different clocks tick at the same frequency, the phase difference between them is constant in time. So if we consider again a minute hand that's at 90 degrees and our minute hand that is at 30 degrees, so this is the one that's at 90 degrees, this is the one that has a phase of 30 degrees, and we found that their phase difference when they're in these positions is 60 degrees. So now let's consider the 2 minute hands on these clocks a certain amount of time later. For example, let's consider them 5 minutes later. So now let's measure the phase of each of the minute hands. So we can see the phase of the first minute hands is 120 degrees. It makes 120 degrees with 12 o'clock. And we can see that the phase of the second minute hand is 60 degrees. So again, we can calculate the phase difference of the 2 minute hands. And we find that the phase difference is equal to 120 minus 60, which is again 60 degrees. So we can see that the phase difference is constant for the 2 minute hands. And the reason this is the case is because the minute hands are both ticking around the clock at the same rate. So they both need to cover 1 minute in a minute because they're defined as minute hands. So this means they both have the same frequency. So they're going to cover the same portion of their cycle in the same amount of time. So which is why in 5 minutes, they both cover 5 minutes. It is not possible to measure the phase difference between the minute and hour hands because they have different frequencies. So if we consider the frequency of the hour hand and the frequency of the minute hand, so frequency of hour hand is F1, frequency of minute hand is F2, we find that the frequency of the minute hand is a lot greater than the frequency of the hour hand. So because this means that in the same amount of time, they will each have covered a different portion of their cycle, the phase difference isn't constant. And the reason they have different frequencies is because if we're considering the time period, the minute hand has a time period of 1 minute and the hour hand has a time period of 1 hour. And we know frequency is the inverse of period. So we can see now why we have two very, very different frequencies. And we can actually see this here. So we can see that here, minute hand is at an angle of 30 degrees. So its phase here is 30 degrees. Then 10 minutes later, its phase is 90 degrees. So it's covered a fair portion of its cycle, whereas the hour hand has barely moved. So we can see that the phase difference is quite clearly not constant. So therefore, we can't measure the phase difference between the minute and hour hands. And this is because the phase difference is not constant in time. So now that we've considered phase and we understand what we mean by phase, we're going to link phase to waves and see how we can express phase in terms of fractions of wavelength. The distance travelled by a wave in one oscillation is equal to its wavelength. So this red box here shows one oscillation of a wave. And we measure wavelength as the distance covered by that wave in one oscillation. So that's what we've got here. This is the wavelength of the wave. Circles are well suited for representing waves. One revolution around the circumference of a circle represents one oscillation of a wave. So again, in this red box, we have one oscillation. We've said the wavelength of a wave is the distance covered in one oscillation. And we can consider one revolution around this circle's circumference as one oscillation of a wave. So again, within that one oscillation of the wave will cover a distance equal to its wavelength lambda. The phase of a point on a wave is the portion of an oscillation it has completed. So here we have a wave. And because we're comparing a one wave cycle to one revolution around a circle, we consider one wave cycle to have a phase of 360 degrees. So one oscillation has a phase of 360 degrees. And that's because one revolution around this circle has an angle of 360 degrees. So if we go from 0 degrees, we're defining this orange point here as our origin, and we go around the circle once, which is corresponding to one oscillation, we've covered 360 degrees. So that's why we have a phase of 360 degrees for one oscillation. So that means for half an oscillation, we have 180 degrees, and that corresponds to going round half of this circle here. Then a quarter of an oscillation corresponds to 90 degrees, and that corresponds to going round a quarter of this circumference. And then if we were to cover 1.5 oscillations, which is what we've got here, that would involve going round this circle once, and then going round it a second time. So that corresponds to 540 degrees, and therefore corresponds to a phase of 540 degrees on the wave. One full orbit around the circle corresponds to the distance of one wavelength travelled by a wave, or a phase of 2 pi. So we were saying that one oscillation corresponds to a phase of 360 degrees. So one oscillation covers a distance of one wavelength, lambda. So we can also write this phase in terms of radians rather than degrees. So we know 360 degrees corresponds to 2 pi radians. So we can therefore say that one oscillation has a phase of 2 pi radians. And that's the same as completing one revolution around this circle. We know that the angle going around a whole circle is 360 degrees, or 2 pi. So that again corresponds to the phase of one oscillation. Then half an oscillation has a phase of pi, 1.5 oscillations has a phase of 3 pi. And again, that would correspond to going around the circle once and then an extra half time. We can calculate the phase at a point on the oscillation using the distance from the origin in terms of the wavelength. So we know that one oscillation corresponds to one wavelength, and we can split one oscillation into quarters. So that therefore is split into quarter wavelengths. So we can have lambda over 4, lambda over 4, lambda over 4, lambda over 4. So we've split our oscillation into quarters. So now let's consider the position of the green dot. We can see that the green dot has covered 3/4 of the wavelength. So that's what we can write in here for its distance, 3/4 lambda. So if the green dot is 3/4 of the wavelength, and one wavelength corresponds to one whole revolution of the circle, we can therefore see why the green dot here is at 3/4 of the circumference. So if this is our origin, a quarter of the circumference corresponds to a quarter of a wavelength, half corresponds to half a wavelength, 3/4, which is where the green dot is, corresponds to 3/4 of a wavelength. And in terms of phase, this corresponds to a phase of 135 degrees. We can describe the position within a cycle in terms of the phase or in terms of the distance travelled as a fraction of the wavelength. So first of all, let's consider the phase of certain wave cycle positions in terms of degrees. So at the origin, we have a phase of 0. At a quarter cycle, we have a phase of 90 degrees. At half a cycle, we have a phase of 180 degrees. At a full cycle, we have a phase of 360 degrees. Remember, 360 degrees corresponds to a full circle, and we've said one wave cycle corresponds to one revolution of a circle. Then 2 full cycles is going to be twice the phase of 1 full cycle, so 2 full cycles corresponds to 720 degrees. So now let's find the phase in radians. So at the origin, again, we have a phase of 0. At a quarter cycle, we have a phase of pi by 2. At half a cycle, we have a phase of pi. At a full cycle, we have a phase of 2 pi. Again, this comes from the fact that one full cycle corresponds to one full revolution around a circle circumference. And we know that the angle represented by a whole circle is 2 pi. So that's why one full cycle has a phase of 2 pi. And then if we look at 2 full cycles, the phase of 2 full cycles is going to be given by twice the phase of 1 full cycle, which is 4 pi. So the reason we usually tend to express phase in terms of radians rather than degrees is that we can see that adding up degrees produces quite large numbers, whereas adding up radians doesn't produce such big numbers. So it actually makes it easier to use radians because we're not dealing with such big numbers after a lot of oscillations. And finally, let's consider the number of wavelengths. So at the origin, we have 0 wavelengths. At a quarter of a cycle, we'll have covered a quarter of a wavelength. Remember, one full cycle corresponds to the distance travelled by the wave in one wavelength. So in half a cycle, the distance covered by the wave is going to be half a wavelength. Then we've said the distance covered in one full cycle is equal to the wavelength of the wave, and obviously 2 full cycles will cover twice the distance that 1 full cycle covers, which is twice the wavelength. So now that we understand what we mean by the phase of a wave and we know how to find the phase of a wave, we're going to look at what it means for 2 waves to be in phase, out of phase, or in antiphase. If 2 points oscillating at the same frequency reach their maximum positive displacement at the same time, they are said to oscillate in phase. So for example, if we consider 2 children swinging on a swing, and we consider their position at one instant in time here, we can see that they're both at their maximum positive displacements. So that's what we're representing here with the green and red circles. So we're imagining that these are modelling the 2 children, and we can see that because they're both at their maximum positive displacement at the same time, that's what we can see in this snapshot, we say that they're in phase. But if 2 points reach their maximum positive displacement at different times, they are out of phase. So now let's consider 2 children swinging on a swing, but let's consider them at a different instant in time. Now we can see that one child is at its maximum displacement, but the other child is not at its maximum displacement. So this means they're both out of phase. If one point reaches maximum positive displacement as another reaches maximum negative displacement, the points oscillate in antiphase. So now let's consider the 2 children at this different instant in time. We can see that this child here is at his highest point on the swing in one direction, and that this child here is at its highest point in the swing but in the opposite direction. So we say that the first child has a maximum positive displacement, and the second child has a maximum negative displacement. So we're still using the red and green circles to represent the children. Different points along the same wave oscillate at the same frequency and can oscillate in phase, out of phase, and in antiphase. So if we consider the red and the blue circle here, we can see that the red circle is at a maximum displacement and it's at a maximum positive displacement, whereas the blue circle is at a maximum negative displacement. So we can see that these 2 points are oscillating in antiphase. However, if we consider the red circle and the green circle, we can see that they're both at a maximum positive displacement at the same time. So these 2 points are oscillating in phase. These terms can also be used to describe 2 different waves of the same frequency which overlap. So if we consider these 2 waves here, we've got them on a displacement time graph now rather than a displacement distance graph. And we know that the time period for a wave is given by the time taken for it to complete one full oscillation. So in this case, this arrow here shows us the time period of this wave, and we can see that this bottom wave has the same time period. And we know that the frequency of a wave is given by 1 divided by its time period. So if both waves have the same time period, that means they must both have the same frequency. So since these waves both have the same frequency, we can compare their positions and see whether they're in phase or out of phase. So similar to how when we were looking at the minute hand and the hour hand, we couldn't find the phase difference because they were moving at different frequencies, it's the same case with waves. It's helpful for us to compare the phase of different waves when they have the same frequency. At a point of intersection, 2 waves oscillate in phase if they are at the same stage of the oscillation as time progresses. So we're going to consider the waves at a point of intersection. So we're saying at a point of intersection of 2 waves, they will be oscillating in phase if they are at the same stage of the oscillation. So to consider this for 2 waves, we need to look at their positions at certain times. So for example, let's consider a time t1 here. So we can see these 2 points on the waves at a time t1 are both at a maximum positive displacement. So at t1, they're both at the same point in their oscillation. Now let's consider what happens at a time t2, at this point here. So we can see at a time t2, both points on the waves are at a position of 0 displacement. So we're looking at these points here. And they both have 0 displacement at time t2. So far we can see as time progresses, the 2 waves are at the same stage in their oscillations. So now let's look at what happens at a time t3, which is here. So we're considering these 2 points here, and we can see at a time t3, both points are at a maximum negative displacement. So we can clearly see that as time is progressing here, at this point of intersection, both waves are oscillating in phase. And that's because they're at the same stage in their oscillation at the same time. At a point of intersection, 2 waves oscillate in antiphase if they are half an oscillation out of phase as time progresses. So now we're considering 2 other waves at a point of intersection here. So let's consider the positions of both waves at a time t1. So this is our time t1, and we're going to consider this point and this point here. So we've got our points shown in this diagram. So we can see that one point is at a maximum positive displacement, whereas the other point is at a maximum negative displacement. So far it looks like the 2 waves are in antiphase. However, let's consider what happens at another point in time. So let's consider a time t2. So at t2, we can see that the first wave is at this position here in its cycle, and the second wave is at a different position in its cycle. So at t2, we can see that the first wave is now at a maximum negative displacement and the second wave is at a maximum positive displacement. So we can see that at both times here, t1 and t2, one wave has a maximum positive displacement, whereas the other has a maximum negative displacement. So we can clearly see that both these waves satisfy the condition for oscillating in antiphase. If the 2 waves overlap along the same direction of propagation, the waves align in space if they are in phase. So now we're considering every point along these waves as a point of intersection. And what we can see here is that when the 2 waves intersect, they are intersecting at the same point. So when this point intersects with this point, we can see we've got 2 peaks. So the points that are at the same position along the wave also have the same displacement within the wave cycle. And that's the same case for these 2 points, and also for all these troughs and all the peaks and all the points of 0 displacement. So all the points are overlapping, which means these 2 waves are in phase. So this is how we can see that they're in phase if we're considering displacement distance graphs. So they're overlapping along the same direction, and we can clearly see that they're aligned in space. So that's why we say that they're in phase. Now, waves overlapping along the same direction of propagation that are out of phase do not align in space. So again, we're considering 2 waves here that are overlapping. However, in this case, we can see that the points aren't aligned. So this peak here is not aligned with this peak. We can see that there's a phase difference. So we can see we've got this phase difference here between them. And that's the same case with these 2 points. So we've got this point here and this point here. And again, they're not aligned. We've got this difference between them. So because these waves aren't aligning, we say that they're out of phase. If the overlapping waves are in phase, the peaks of one wave will align with the troughs of the other. So now we're considering 2 waves that are in antiphase, and they're overlapping here. So you can see that these 2 waves are overlapping along the same direction of propagation. However, in this case, when we consider the peak of this wave, we can see that it's aligned with the trough of the other wave. And when we consider the trough of this wave, we can see it's aligned with the peak of this other wave. So we've got a trough here that's aligned with a peak here. So in this case, we say that the waves are in antiphase. Now that we know how to find the phase of a wave, and we know what we mean when we say that 2 waves are in phase or in antiphase or out of phase, we're now going to think about how we can find the phase difference between 2 waves. The phase difference between 2 points on the same wave depends on the distance between the points. So if we're considering this wave here, and we're considering the phase of the wave along this x-axis, in order to find the phase difference between 2 points, we need to know their distance. So we need to know the distance d here. And if we remember, when we're talking about the phase of a wave, at the beginning of the oscillation, it has 0 phase. Half an oscillation has a phase of pi. A whole oscillation has a phase of 2 pi. 1.5 oscillations have a phase of 3 pi. And then 2 oscillations have a phase of 4 pi, and so on. So if we want to find the phase difference between 2 points, we need to consider the distance between them, essentially. We can calculate the phase difference between 2 points using their separation along the wave and the wavelength of the wave. So if we want to find the phase difference between 2 points, we need to do the distance between the 2 points divided by the overall wavelength and then multiplied by 360 degrees. So when we're finding the phase difference between 2 points, we want to know what the phase is between them. So to do this, we need to consider the distance between them, d, divided by lambda. So what this tells us is it tells us the fraction of a wavelength that they have between them. And if we then multiply this fraction of a wavelength by 360 degrees, we're able to get the phase difference. So this equation here will give us the phase difference between 2 points in degrees. So that's the phase difference in degrees. We've said d is the distance between the 2 points, and lambda is the wavelength of the wave, of course. So we know the wavelength of a wave is given by the distance travelled by one oscillation. So that's the wavelength of our wave, lambda. And we want to do the distance between the 2 points, which is shown by this arrow here, divided by lambda multiplied by 360 degrees. And there's also an equivalent equation to calculate the phase difference in radians. So we can also find the phase difference between 2 points in radians. So now, rather than writing 360 degrees, we're going to write 2 pi, because we know that 360 degrees corresponds to 2 pi radians. Then the rest of the expression is the same. We just do d divided by lambda, where again, d is the distance between the 2 points, lambda is the wavelength. So this equation here will give us the phase difference of 2 points in radians. We can see that if the distance between 2 points is equal to 1 wavelength, the phase difference is equal to 360 degrees, or 2 pi radians. So this blue arrow here shows us the wavelength of our wave, and here we're going to consider the distance between the blue point and the green point. We can see here that the distance between the 2 points is also a wavelength, so d is equal to lambda in this case. And that's because we can see both points are in the same point in their wave cycle and they're in adjacent wave cycles. That's why they've got a distance of lambda. So if we want to calculate the phase difference of these 2 points, we're going to do 360 degrees multiplied by lambda divided by lambda, because in this case we can see the distance between the 2 points is lambda. So this gives us a phase difference of 360 degrees. So if they've got a phase difference of 360 degrees, this shows that one point is one whole cycle ahead of the other. That's why they've got a difference of lambda between them. So now let's find the phase difference in radians. So the phase difference is going to be equal to 2 pi, again multiplied by lambda divided by lambda. And in this case, we're going to end up with a phase difference of 2 pi radians. So again, 2 pi radians means that one of the points is a whole cycle ahead of the other. And again, this is because they've got a distance between them equal to 1 wavelength.
Hey guys, I hope you enjoyed the video. If you're looking for an amazing A-level physics resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face and together, let's make A-level physics a walk in the park.